Today we are talking about X-rays. As I showed in my video about analyzing the technetium sample that I bought online, measuring X-rays is another non-destructive analysis method. For this, we use this device here. To avoid any confusion, as probably mentioned in the title, we are doing XRF, which is X-ray fluorescence analysis. This is different from what they do in hospitals. So, the device is cooled with liquid nitrogen. It needs to be cooled for measurement, but between measurements it can warm up. From there, a cryostat runs to a detector covered with a beryllium foil. We also 3D printed a sample holder for two reasons. During the measurements, no light should enter and the beryllium foil is extremely thin, so we wanted to minimize the chances of accidentally damaging it. Now, those familiar with such XRF devices might wonder, okay, but where is the X-ray source? XRF, X-ray fluorescence, meaning excitation by an external X-ray source. And then the fluorescence of the sample is measured. Yes, there are such devices too. I'm even going to make a video about it, where we use this to analyze ancient coins. However, the samples we measure in nuclear chemistry are all radioactive, meaning they practically generate their own XRF. How is it measured? Again, it's a semiconductor detector, which in our case is connected to the measurement electronics. The detector is set up to -400 volts, which is why it's connected to the 0 to 500 power supply at output A. On the other side, you can see it again, negative light is on and the dial is set to 0.4 kilovolts. And you don't see anything on the display. This is because 1 bar stands for 500 volts, which hasn't been reached yet. The signal from the detector is fed through the linear input into the preamplifier and then through a cable to the multi-channel buffer MCB. The MCB then sorts the pulses by energy and sends them via USB to the computer. For those who've zoned out, this part is really just for me in case someone plugs it out and I need to know how to plug it in again. Now onto the samples. We have thorium metal powder, a uranyl acetate crystal, a cesium-137 gamma calibration source, another one with americium-241, a radium calibration source, uranium dioxide pellets, a gold plate with technetium on it, and a uranium mineral sample that ultimately wasn't suitable for the measurement as it's just too big. Place the sample into the spectro cup, put the lid on and off we go. Here's the spectrum from cesium-137, recorded over 5 minutes with a dead time of 12% because it's way too active for a simple calibration. So we see some lines here, but what do they represent? First, a brief definition. In a broader sense, X-rays are lower in energy than gamma radiation. You can also see that on the Wikipedia graph. This is a very commonly used definition. But in a stricter sense, X-rays is defined as high energy electromagnetic radiation originating from the electron shell, whereas gammas originate from the nucleus. This means in the rare case of like thorium-229M, gamma radiation emitted from the nucleus could have been in the UV range when it comes to energy. Personally, I do not care which definition you use, as long as it's clear what's being discussed. For 99% of the cases, the broad and more widely accepted definition is sufficient. However, I just wanted to point out that two different definitions of X-ray and gamma radiation exist. Back to cesium-137. It's a beta-minus emitter and decays 95% of the time into barium-137M. This means we have an excited daughter nucleus that needs to release its energy somehow. It can do this by emitting a 661 kiloelectron-volt gamma quantum, but it doesn't have to. There is also a competing decay mode called the isomeric transition via internal conversion. Here the excitation energy of the nucleus is transferred to an inner electron. The electron in the K-shell has a minimal probability of being inside of the nucleus, and the energy is transferred to this K-electron via a virtual photon, causing it to be ejected with 624 kiloelectron volts. Now we have barium-137G with a hole in the K-shell. This hole is filled, and if it's filled from a L2 level, the electron must lose the energy difference between the K and the L2 level, which happens through the emission of a 31.8 kiloelectron volt quantum. The L3 level is slightly higher, and if it's filled from there, a 32.2 kiloelectron volt X-ray is emitted. If the hole is filled from the M level, the energy difference is 36 kiloelectron volts. The probability of internal conversion from barium-137M where the K electron is emitted as a conversion electron is 7.79%. Now this explanation doesn't apply to technetium-99, it mostly decays into the ground state of ruthenium-99, so no internal conversion. How do X-rays come about here? Well, it could be that during the decay of technetium, we end up with a ruthenium-99 nucleus that has such a high recoil that it ionizes the K or the L electrons. It's highly unlikely, which is why the probability are so low, so surely the higher electrons in the N or O shells can be ionized more easily. But the transition no longer fall within the X-ray range. After 30 minutes of measurement, we can already see the ruthenium KL3 line at 19.2 kiloelectron volts. So the recoil happens, but we also see technetium X-ray lines at 18.3 kiloelectron volts. A technetium atom can also ionize another technetium atom through beta radiation. This wasn't visible in the onyx met sample because there's so little technetium, but on our plates we deposited much more technetium. 13.37, 11.4 and 9.7 kiloelectron volt are gold lines, so the beta radiation also ionizes the gold on which the technetium is deposited. These are the L gamma 1, the L beta 1 and the L alpha 1 lines. Alpha, beta, gamma are just different nomenclature again. L gamma is the O to L transition in gold. L beta is the N to L transition and L alpha is the M to L transition. The numbers refer to the fine structure in the shells. Now what happens with an alpha emitter? With thorium it's pretty boring. Thorium has such a long half-life that it's pretty much impossible to see. Even after 30 minutes of measurements, uranyl acetate can also be ignored. With radium-226 we have a bit more activity. And after 6 minutes of measurements we can see a peak at 13.08 kiloelectron volts and one at 15.54 kiloelectron volts. Recoil ionization from radon, polonium or ionization from other radium atoms is either too high in energy for our X-ray detector or occurs with a too low probability. But everything is in radioactive equilibrium, meaning that lead-214 is the first beta emitter that decays into an excited bismuth nucleus, which can release excess energy in the form of gammas or conversion electrons. These are the N to L transitions at 13.02 kiloelectron volts and O to L transitions at 15.25 kiloelectron volts, though that's a bit off. Americium-241, after 3 minutes we have enough to show everything that I wanted, and they are the gamma lines from Americium-241 at nearly 60 kiloelectron volts. You can also see a second gamma line at 26.34 kiloelectron volts and another one with a probability of 0.01% at 33.2 kiloelectron volts. And then we have this forest of line. The excited Neptunium-237 nucleus produces conversion electrons, and as we can see in the isotope browser app, it also does Auger electrons. These Auger electrons are created when X-ray from the sample produced by an L to K transition hits another outer shell electron. So it's basically an internal photoelectric effect, and the electron emitted by the X-rays are called Auger electrons. Excited nuclei produce conversion electrons, and the internal photoelectric effect creates Auger electrons. If those are missing, we again have holes in the shell, and since Neptunium is such a large atom with a higher nuclear charge and so many electrons, many transitions are possible, which are all still within the X-ray range. In fact, the simplest transition from L to K happens at 96 kiloelectron volts. So we have a complex mix of shell transitions. For all these data, I used the NDS web or the isotope browser app and deliberately decided to not use the original recording from me searching within the database. That would have been a bit too much back and forth. That worked with the technetium analysis, but for those interested, the NDS is linked in the isotope browser app, is available for free for Apple and Android. This was a tiny glimpse into X-ray analysis in a nuclear lab. X-rays are also used in so many different fields, not only just for broken arms, but also for broken legs, for example. Yeah, this stuff is very interesting, and if you're working with X-rays, feel free to leave a comment what you are using them for. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!